Hi, and welcome back to Hacker 101. In this video, we're going to be talking about the basic concepts of the web and how they affect security, HTTP, HTML parsing, cookies, and more. Then we're going to talk a little bit about CSRF attacks and other related things. Let's get started. Everyone here has probably seen an HTTP request. You can see one displayed below. There are a couple main parts to it. You have your method, get, post, delete, put. You have the request path that's going to be requested, in this case just slash, the root. And then you have a number of different headers, host, user agent, accept, things like that. All of you have probably seen this many times, and if you haven't, you're going to see a ton of them in Burp. But this is the main form of a request. And as I said, the basic format is just verb, resource locator, and then your headers, and then your body. Headers are separated from the body by two CRLF sequences. In this case, here's a breakdown of just a couple headers that are used there and some other common ones. So you have your host header, which indicates which host is actually going to handle that request. You have the accept header, which indicates which MIME types are accepted by the client. That's often used to specify JSON or XML output in the case of web services. If you're making a request to some endpoint and you want to specify that you want XML output, for instance, then you can just send up accept text/XML. The cookie header is able to pass cookie data to the server, and we're going to talk a little bit more in depth about cookies in a few. You have the refer header, which shows you which page actually led to that request. Then you have the authorization header. It's used for basic auth pages usually. There are a couple different forms like NTLM for NT-style logins. The basic auth is what most people use. This does not do any form of encryption or anything like that. Rather, it just has the text basic and then a base64 blob of the username : the password. Basic auth you'll see quite often, and if you do see it in Burp, it's easy to take that base64 blob, throw it into the decoder, and immediately see what the username and password were. So it's really handy to be able to do that. So as most of you know, cookies are just key value pairs of data. They're stored on the client for a fixed period of time. Sometimes those periods are very long, but it's always a fixed period. And those come from the server or are added by JavaScript, and then are sent up with each request to the domain that they're scoped for. Each cookie has a domain pattern that it actually matches. Sometimes that's very specific. Sometimes it's matching a root domain, and it'll apply to any subdomains. This has security implications in that cookies are going up to one place where they shouldn't be, then you can have some nasty things here. Likewise, if you can set cookies on domains where you're not supposed to, that would also be a breach of security. So how are cookies secured? Well, there are a couple simple rules for how cookies actually work. Cookies added for .example.com can be read by any subdomain of example.com. Cookies added for a subdomain can only be read in that subdomain and its children. A subdomain can set cookies for its own subdomains and its parent, but it can't set cookies for sibling domains. What that means really is that, let's say that you have the subdomain text.example.com. It can set cookies on example.com, because that's its parent, and it could set cookies on foo.test.example.com, which is its child domain, its own subdomain, but it couldn't set them on test2.example.com, because that's a sibling domain. You have to keep that hierarchy in mind when you're thinking about the scoping of cookies, and that's something that you're going to see people mess up a whole lot. You're going to see people scoping cookies where unauthorized code or insecure code potentially is running alongside secure code and can access the same cookies and manipulate the cookies of parent domains or subdomains. So that's something that you really need to keep in mind. In addition, you have two flags that you can apply to cookies, and these are sent when the server actually sends a cookie down to a client. And those are secure, which means that the cookie will only work on HTTPS pages. It'll never be sent up in pure, plain HTTP requests, only HTTPS. And then the confusingly named HTTP only cookie, which doesn't do the opposite of secure. What it does rather is make sure that it only sends the cookies up with web requests. It won't allow you to read those cookies from JavaScript. Normally, you can use the document.cookie variable in JavaScript and actually get a list of all the cookies that are applied, or that are in scope, I should say. And you can also manipulate them that way. But with the HTTP only flag, they'll only be sent up in requests. They won't show up in JavaScript. And if I recall correctly, setting those in JavaScript will not actually set those values. So those are applied in the set cookie header that actually sets those. Now let's talk about HTML a little bit. It seems non-obvious that HTML would actually be an important thing to learn about in this class, just because everyone here has seen HTML. You've probably seen it many, many times, probably every day. But there are a couple weird quirks about HTML that most people don't think about in a security context. For instance, what spec you parse HTML against actually really matters. Generally speaking, that's going to be HTML5 for most sites now, or at least most modern sites. But the thing is that HTML isn't just parsed by your browser. It's also parsed by things like web application firewalls, which sit in front of an application and look for things like cross-site scripting and things of that nature. If they're parsing HTML in a different way than your browser is, if there's any discrepancy between the two, that will often result in a security vulnerability that you can exploit. The canonical example here is a pretty simple cross-site scripting vulnerability. Instead of just a script tag that has alert1 in it, in this case we have a script that has a source. But here's the interesting thing here. Instead of just script as the tag name, we have script/XSS. What that will do in a browser is absolutely nothing. It will parse it as a script tag, it'll treat the slash as white space, and you'll end up with an empty XSS attribute on that tag. But a web app firewall that is improperly parsing HTML, which is most of them, will see that as a script/XSS tag, and it'll let it straight through the filter. Nowadays, they've gotten better. Usually they're not quite this dumb, but they're still pretty dumb. And really, it's an uphill battle where every time there's a simple discrepancy between the HTML parser in the browser and in a WAF or other intermediate, you're going to have nasty problems. And you're going to see this pop up time and again. The other thing is that browsers are built to handle the web, obviously. If a browser doesn't work for most web pages, it's going to have some problems. And most web pages are broken in some way or another. So there's a lot of legacy parsing in browsers. And in HTML5, there's actually specifics on how that legacy parsing should happen. We're going to talk a little bit more about this in the XSS session, but here are two really good examples of how this can work. If you have a script tag on its own, the browser will automatically close it at the end of the page. You may end up with some syntax errors in there, but that's fine if it's automatically closed. This seems irrelevant if you've already got the ability to add HTML into the page, but let's say that it's a cross-site scripting in the URL, and you can't get a slash in there because it's parsed as a path separator. This is a case that I've seen on a number of occasions, and that's something that you really have to keep in mind. In addition, a tag that's missing its closing angle bracket will usually be automatically closed by the angle bracket of the next tag. It will end up with a lot of irrelevant attributes and some funkiness in there, but having an open angle tag inside of another tag is valid according to most browsers. And this again can throw off things like web app firewalls. An old trick was to actually wrap script tags an additional set of angle brackets, which would get it right through a web app firewall and parse properly in the browser. So keeping in mind these weird discrepancies in HTML parsing and how you think about things is a really good way to actually find ways to get around filters. We're going to talk a ton more about filters very shortly. Now, some of you may know about content sniffing. Content sniffing is where you can send data to the browser without giving it all the information about what it is you're sending it, and it'll sort of fill in the blanks. Examples of this are MIME type sniffing, where it tries to figure out what type of file you're sending it, encoding sniffing, where you're checking what sort of text encoding you're sending it, so ASCII, UTF-8, Shift.js, whatever. It'll sniff the content to see if it matches certain heuristics, and then it will use those behaviors inside of the browser. MIME sniffing is one of the ones that used to bite a lot of browsers. It's not so common anymore, at least not as a security relevant issue. But the browser will often not just look at the content type header. It'll also look at what's on the page. If it has enough markers that make it look like HTML, the browser will treat it as HTML. In IE 6 and 7, there were cases where image and text files that didn't have proper MIME types sent down and contained enough HTML would actually execute as HTML. So you could get cross-site scripting in a stored fashion very trivially on IE 6 and 7. Obviously, those are old now, but you still find these installed. In enterprises, IE 6 and 7 bugs, still a big issue. So these are still things that you should look for where you don't have appropriate MIME types and really know how to detect them and how to actually prevent those. So imagine you have a site with file uploads for profile pictures, say Facebook. If that file that you upload contains just enough HTML to trigger those sniffing heuristics, an attacker could upload a picture that contains a lot of HTML and then just link it to their victims as an innocent picture. At that point, they're able to execute anything the user can in the context of where that file was uploaded. This is one of the reasons that Facebook and other sites use separate domains to host pictures and videos, everything like that. And we're going to talk a little bit more about separate domains in a moment with same origin policy, which is what really governs cross-domain accesses. So I mentioned encoding sniffing, and here's a really weird case. You have pages with all different sorts of content on them all the time. A lot of you came from Hacker News. Hacker News doesn't convert everything to the same encoding type, so the browser will actually see, okay, I have a character that doesn't make sense in this encoding. I'm going to try and sniff it instead. And you'll end up with a page with a bunch of mangled symbols. Happens pretty often, even in modern browsers. If you don't specify an encoding, the browser will automatically apply these heuristics. And if you can control the way that the browser decodes text, you may be able to alter the parsing, and you can also get around filters. A good example is putting UTF-7 text into cross-site scripting payloads. Now, most people aren't familiar with UTF-7. It's not very common. UTF-7 is basically 7-bit ASCII with embedded base64 blocks for extended range characters, so any of your Unicode characters that don't fit into 7 bits. You basically have a base64 block that's blocked off with a plus and a minus, and that will decode to that character. So you can see the payload there is really just a script tag with an alert in it. This will go straight through HTML encoding. So if you throw this on Facebook, it will go there no problem. There are no unsafe characters there. But what there are unsafe UTF-7 characters. IE8 and below, along with Opera, earlier versions of Firefox, things like that, will see that in a page and automatically switch the parsing to UTF-7 mode. And then those will just be decoded like any other character. This can be an effective way to get around firewalls, web app firewalls specifically. Because if they're looking for, say, angle brackets and double quotes, standard characters that we always filter out, they're not going to be looking for UTF-7. Same thing goes for if they're expecting ASCII, just plain ASCII or UTF-8. You send it UTF-32 characters, you're going to get straight through the filter there too. I had a client that was trying to sanitize XML coming from unauthorized sources, or rather untrusted sources, and they didn't take into account the fact that they could specify different XML encodings. So I started sending up UTF-32 and things like that, and it would go straight through the filters where they were trying to sanitize this XML. Similar case happens here, except that the encoding is automatically determined by the browser if you don't specify an encoding. So, the rule here is you should always be specifying an encoding and know what encoding the browser should be parsing it in so that the server and the client don't have a discrepancy. Same thing goes for MIME types. Always specify MIME types, no matter what. Even if you're just sending an octet stream, always set MIME types, no matter what. So same origin policy is really the backbone of web security today. Without same origin policy, you wouldn't have the ability to move data between subdomains. You wouldn't have locks between separate domains, things like that. It is really what underpins browser security now. So what is it? It's what domains you can contact via XML HTTP request, AJAX requests as we normally call them. It also restricts access to the DOM across frames and windows. So if you open up a new window with JavaScript, you may or may not have access to the DOM in that new window. What determines that? Same origin policy. This is what prevents you from making AJAX requests across domains, with the exception of CORS requests, which we're also going to talk about in a few minutes. Same origin policy is really what prevents you from wreaking havoc on the web. And any time that it's circumvented in some way, bad things happen for just about everyone on the web. So there's this concept of origin matching in SOP. And it's much, much, much more strict than cookies are. First of all, the protocols must match. You can never cross the HTTP/HTTPS boundary, ever. Port numbers must match. Usually these are, 80, 443, whatever. And then domain names must be an exact match. There's no wildcarding. You can never go up or down subdomains, any of that. It must be an exact match. Now, it is possible to loosen SOP. So, you can change document.domain in JavaScript. And that will allow you to change which subdomain, in essence, you are able to communicate with. And there are a number of rules around this. You can also do message posting with the post message function, for instance, in JavaScript. And then you have CORS, which again we'll talk about in just a moment. These all open up a lot of different interesting avenues for attack. They all open up things that you would never expect. For instance, you can always call post message into an iframe. How many sites that actually receive messages validate them properly? The answer, pretty much none of them. Mind you, it's a rare thing to actually see this happen. But when you do see message handling inside of a web app, they almost always handle it wrong. In addition, this was used to break a lot of Chrome extensions. Chrome extensions are very limited in what they can do inside of their sandbox, so they use post message to move around. Because you're able to always post to these extensions, because of the way that they break the sandbox in effect, they were vulnerable to cross-site scripting in a lot of cases. And this could even be used to jump from one web page or one tab to another through these extensions. This has been a source of pain repeatedly, and no one really has any decent solution. Generally speaking, if you don't have a very, very good reason to do it, you shouldn't loosen the SOP. There's usually a design problem there if you're trying to do that. So, CORS is cross-origin resource sharing. Basically, it allows you to make requests across domains outside of SOP using XML HTTP requests. CORS also comes into play with WebGL in that it can read textures across domains. But CORS is still really new, and it enables some kind of risky situations. What's interesting is that you can actually make it past receiving domains cookies. So if you make a request from foo.com to bar.com, and bar.com actually has the CORS headers, you can make it send the proper cookies on bar.com up to that server. And you can't access those yourself, but you can potentially compromise logged in users. And really, this just hasn't been explored. People have played around with CORS. It's fairly well designed, but it's still very much new territory. And it's something that I really encourage you to look into and play around with a little bit. You're going to see some examples in your coursework, but there are a lot of things that just haven't been touched yet. So I recommend that you just go and explore maybe a little bit later in the course as you get more advanced as a breaker. Now let's talk about CSRF attacks. These are one of my all-time favorite vulnerabilities. It's simple and you find it everywhere. Usually if you find one in an app, you're going to find it systemic. You're going to find that they have no prevention against it. And this isn't an uncommon thing. I would say probably 1 in 5 or 6 apps that I test fall prey to CSRF, at least in one case, generally more than that. So what is it? Cross-site request forgery is basically when an attacker can get a victim to go to a page that they control, and then it submits data to some target site as the victim. It's excruciatingly common, and it's brutal. The canonical example is a bank transfer site. Here we have this form that allows transfers from one account to another. And it's very simple. You have a post up to some level. You have the to variable, which has your destination account. You have the amount that's being sent, and then you have a submit button. That's it. So when the server gets such a request, how can it know that it actually came from the real site, that they actually went to that form and entered the data? You have the referrer headers, as I mentioned before, those come up in the HTTP request, but they're unreliable at best. At worst, they're forged. Here we can see an actual exploit that will transfer money if the user is logged in. It's, again, a very simple form. It has 2 hidden inputs, an amount and 2, and it transfers from one account, whatever account the user is logged into, to account number 1625. Transfers $1 million into that account. And that happens instantly because when the body loads, it automatically submits that form. So how does the server tell that this request is any different from a normal request that a user would make, even though the user had nothing to do with this transfer? That's the big question with CSRF. And the answer is, it can't. So clearly we need to give the server a way to know where the request originated from. Did it originate on its page or somewhere else? The way that this is traditionally done, and it's traditional because it works, is to mitigate the bug through the use of CSRF tokens. Basically, all you have to do is just generate a random token, tie it to the user's session, and then embed it in each form that you generate. Every single form that you generate is going to send up an additional input of that CSRF token. Here you can see a form that actually contains that CSRF token. It's a 32 nibble token, plenty of randomness, so you're never going to guess it, and it's just sent up as a hidden input. Whenever the server gets a post request, any post request should always check to see that the CSRF token is present and that it actually matches the token that's in the user session. The interesting thing here is that this all hinges on posts being the only time that you're changing state. GET requests should only ever give you data. They should never actually change data. As you're going to find out if you ever just run an automatic scanner against an application, applications change state with GET all the time. This is something that is very pervasive in the web development community, despite it being a code smell everywhere. It's something that you're going to find all the time, and it is really just quite nasty. So if they're doing that, even if they're checking CSRF tokens on every post, if they're changing state inside of GET requests, they're automatically broken. It's just not going to work out very well for them. I've seen a number of apps do this now, where they implement dynamic CSRF proof forms, as I like to call them. Basically, instead of every form having to have a CSRF token baked into it on the server, which it requires you to put it into the form, it requires you to generate these pages anew every time on the server. You can't cache them except per user, because they do have a user-specific token in them. Instead, what they would do is they would load up a file from the server, we'll call it CSRF.js, and they would load this into the page, which would really just add a variable onto the page, or into the page's scope, with the CSRF token. And then it would walk over all the forms on the page and add the CSRF token to them, which seems like a great solution. You're adding the CSRF token there. But if you have a CSRF token just sitting in a JavaScript file, what's to stop an attacker from just adding that to their exploit? If you give away the CSRF token in some way, you've automatically broken the protection. So as an attacker, this is a really handy thing to have. And I can think of at least 3 or 4 cases at this point of seeing this sort of dynamic CSRF protection in action. And every time it's just as broken. So, just a quick wrap up. To review, cookie domain scoping is often a source of trouble. As we've seen, there are 3 real core rules, but nobody gets it right. So what I encourage you to do is just open up Burp as before, and just start browsing the web. And if you log into a couple pages, I bet you that you'll see some that are scoped to sort of weird domains. You know, they won't use a specific authorization subdomain, despite that they're running a bunch of different apps on one domain, things like that. That sort of scoping can often mess you up. The same origin policy is strict, but it's very complex in a lot of ways. And what that does is it makes things very nice for a developer in that you can actually fine-tune the way that things work. But it also makes it difficult to know how the application is being secured. And CORS really mixes that up, as do the ways to loosen SOP. And then cross-site request forgery is when an attacker tricks a victim into going to a page, which triggers requests on another site. Always use CSRF tokens. If you don't see a CSRF token in a form, even if it's a form that doesn't really do anything, that should be a finding, no matter what. Maybe a low severity, but generally for me, CSRFs are at least a medium, often a high or a critical, depending on what the business impact is. Well, that wraps it up for this session. Until next time, happy breaking.